Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Welcome. My name is Mike Seltzer, and I'm here to happily introduce Kshitij Kumar, who's a PhD student from Carnegie Mellon, working in the robust speech recognition group with Rich Stern, and he's going to tell us all about the work he's been doing, and I think specifically mostly in reverberation,
right?
Which, as we all know, is a very challenging problem. Here you
go. Thanks, Mike. So, as Mike said, the objective of this talk is to provide to study the problem of reverberation and to study reverberation with respect to compensate it for applications in speech recognition. And I'm Kshitij, as Mike said, I'm Kshitij Kumar, I'm from CMU, and my colleagues are, my advisor, Professor Richard Stern, and my colleagues are Professor Bhiksha Raj, Rita Singh, and Changwa Kim. So going forward, we know that speech recognition technologies have considerably matured in the last decade, in the last 20 years. But the problem of robustness of speech technologies to noise and reverberation still exists. And even though many technologies work great in clean conditions or in matched condition, whenever there is a mismatch between training and testing data, the performance is not as good. And the objective of this talk is to make speech technologies robust to reverberation, and then we will also extend the method to noise, and then finally to joint noise and reverberation. Now, before going forward, I'll briefly show what reverberation is, what does it mean, and how does it impact speech recognition accuracy. So, reverberation can be thought of as a superimposition of delayed and attenuated signals. We can think of this as a rectangular room where the microphone here will receive not only the direct component from the source, but the reflections of the wall, and then the reflections of reflections. And over a period of time, we see that we can model this as a linear filter with a room impulse response, and reverberation is characterized by a parameter called room reverberation time. It is the time taken for the signal power to decay by 60 decibel. And as we can see, if the reverberation time is higher in a room, then the signal is the echoes are going to persist for a longer duration of time, and they will lead to greater self interference with the original signal. Now, having said that, this is here I try to figuratively show a spectrum plot for a clean speech and a reverberated speech. So we see that the one clear distinction we see is that the energy spreads, or the energy overlaps into future time segments as we expect it will, and we see that the silent segments here are filled up by energy here, and then the strong voices, the energy from vowels are going to overlap into softer sounds. So the problem is that if we do our training from this, we really not going to do a good job by testing here. And even if we do a matched condition training, even in that case, because the phenomenon of reverberation depends on what the sound which comes before the current sound, so even the matched condition is not going to do very well. We will see those later. Now, this is a speech recognition experiment and on a resource management database, just to see what is the impact of reverberation, how much does it affect speech recognition accuracy. So we see that for clean condition here, training was done on clean condition. So for the speech, the word error rate increases from about 7% to about 50% here, as the reverb time is 300 millisecond, which I think is typical of this room here right now. So if at least for clean condition, this is really a very big problem, and most of the people have in the past speech research, people mostly worked on the noise compensation, but there have not been many solutions or not a lot of study in reverberation. And the focus of this work is primarily on studying reverberation, parameterizing reverberation, and deriving algorithms to compensate for that. Now here I present a brief outline of this talk. First of all, we are going to spend some time in studying reverberation, how reverberation affects speech recognition accuracy, and how can we model that phenomenon directly on the speech features. My claim is that if we can do a good job at modeling reverberation in the feature domain, in the spectral feature and the cepstral feature domain, and directly compensate in the feature domain, then we can build a good system, because because the features are what go to the speech recognition engine. And if we can compensate the features, we are more likely, and the features are closest to a speech recognition engine. So if we can compensate features, this will directly benefit a speech recognition system. So based on that, we propose a new framework to study reverberation first. And then I propose two algorithms. One is called LIFE, another NMF. They use different properties of speech. And then I finally propose a noise compensation algorithm. It's called delta spectral features. And then I propose a joint noise and reverberation model. And I apply my individual compensation for noise and reverberation to jointly compensate for them. And finally, if time permits, I'll talk about an audio-visual feature integration. So before going on to present my model of reverberation, I will present what has conventionally been done in the past. And in the past, we treat reverberation as a filtering in the time domain. And we assume the filter is linear time invariant. And because of that, in the spectral domain, this is multiplicative. In the log spectral domain, this is additive. And also in the Kepstral domain here. So what we are saying is that that convolution in time is multiplicative in frequency, and because of that, it becomes additive in the Kepstral domain. And the model that we arrive is an additive shift model. So we are saying that reverberation introduces an additive shift on the Kepstra. And based on that, the first algorithm, like way back in time, 1995, like that, was Kepstral mean normalization, which tries to subtract the Kepstral mean from a Kepstral sequence, and that will try to remove the reverberation. And CMN is now used in almost all the systems. It is so rudimentary. But the problem is that the speech analysis windows are typically like 25 milliseconds, but the impact of reverberation is like hundreds of milliseconds. So we cannot. So the model here does not apply for a short duration. And to answer that, what people did was that they studied speech analysis. They did speech analysis over seconds, like 1 second or 2 second window duration. And in that, based on the CMN framework, they subtract the log spectral mean, and they do speech reconstruction from there. But a key problem in this method is that because it uses 1 seconds of a speech, this algorithm cannot really be made online, because we have to wait for those many seconds before doing processing further. And so in our work, we ensure that we work from short segments, and still such that methods can be applied in an online fashion, and we can learn some of the parameters which can be used to compensate. Now next, I'll specifically talk about the model that I propose here, the feature domain reverberation model. Now to present my model, I present this framework here. So this is MEL frequency MFCC feature extraction. So what we do is that we take a speech signal SN, we analyze it through a filter bank. They can be like MEL filter or gamma tone filters. We take a short duration power here, we apply log, and then we do DCT, and these features go to ASR system here. And just to note the convention, the output here at the filter bank is labeled little x, the output at power is labeled capital X, and cap XL here, and cap XC here to indicate the two. So what I'm going to do next is to study how reverberation phenomenon which is happening here affects these outputs, these consecutive outputs, and try to derive an approximate model to represent reverberation. Now, as I already mentioned, reverberation happens here, so, and then we'll study the impact of these reverberation at later stages. Now the first thing we can immediately do is that we can, because it's a linear filter, so we can study reverberation at these filter banks, and what we are saying is that signal first passes through each of the filter and then goes to the filter bank. And now note that the labels have changed. This signal is no longer little x, this is little y, and similarly capital Y. So the purpose is to relate little y with little x and capital Y with capital X, as mentioned before. Now the first thing we can immediately do is that because these two are filters, we can switch the two, we can commute the two, and then we have an immediate relationship between little y and the little x here, so it's just filtered by this filter, room response filter. So the representation that we have is like here, and next we will study the effect of this H filter at the power domain. And to do that, and similarly we will study the effect of this little filter at each of these different domains. So to do that, now, so this is the problem that we are right now. We are studying the effect of H filter for the power domain here. Now we start from this equation, which is a linear convolution expression here, and we take y square because we have to take power, so we take y square and then some y square over a short duration, 25 millisecond, like that. Now we can split this term into two components. These are like self terms of x, and these are the cross terms of x. And then we take an expectation, and finally we will still have two terms, one term corresponding to x square, another term corresponding to the cross terms of x. And what we find in principle is that we can ignore this cross term here. We can consider that as an approximation error in my model and just retain this term here. And what that effectively does is that it sort of linearizes the problem. We are saying that y square is a convolution over x square, and if we take a short duration power, it will still remain so. And essentially what I am doing is that I am replacing this filter here as an equivalent filter here, but this filter operates on the cap xs sequences, and I am saying that cap yx sequence is a filtering operation over cap xs sequence with an approximation error. Now that was all said and done, but I'd like to show how good this approximation is. So here I plot this line here is for the clean signal without reverberation. So, and this blue line here is the reverberated the cap xs for the reverberated sequence, the cap ys actual, and the red line is my approximation here. So if my approximation is good, then the approximation should hold on, and it should follow the red line should follow the blue line here. So we see that even though there is an error here, this approximation with respect to speech recognition error accuracy, this approximation is not that bad, and I'm still able to follow the contour. And the big benefit that I get is that I have linearized the problem, and I have a representation of cap yx, the spectral power of y with respect to the spectral power of the clean speech. Now the model that we have so far is, I'm saying that I can equivalently obtain my cap yl by cap ys by filtering cap xs. So this is kind of the model that we have achieved now, and now we will further study the operation of log in the DCT. Now starting from this equation here, which as I derived is a linear equation, is a convolution expression here, I can formulate the problem in a Jensen's inequality framework, and without the details what I achieve is this expression here. So what I'm saying is that the cap yl can be written as a constant plus a convolution over cap xl plus an approximation error here, and this also linearizes the problem and adds. Now the problem is not completely linear because of this term here, and this is the model that I have derived so far, and this is again the same thing and the approximation error. So I would like the red line to follow the blue line here. So again there is an approximation error, but it does a good job at following the contour and trying to formulate the problem so that we can derive de-reverberation algorithms in an easier framework. Now this is the model that I have so far. I'm saying that this is the log spectral model that was derived, and this operates on this log spectral output. Now the same thing can be done on the DCT. DCT is anyway linear operation, so there is no problem. And finally what we arrive is this model here. So I'm saying that the Kepstrel sequences can be obtained by passing the original Kepstrel sequence through a filter and then adding a constant to that, and the next work will actually build on this model. Now we can compare this with the previous model, what was done previously. So previously, as I said before, it's an additive model. So we can see that I'm introducing this new term here. So I'm introducing a filtering first and then a constant additive shift. And this can also be compared with a past work from our group, and but this model applied in the time domain sequence. But now I'm saying that I can equivalently have the same framework, like a filtering plus a noise plus an error term in the Kepstrel sequence as well, where the approximation error is small. The constant C delta can be removed by applying Kepstrel mean normalization, and next I have to worry about removing mitigating this filter term here. Now I'm going to propose two algorithms: the LIFE, it's a likelihood based inverse filtering approach, and the NMF approach. So first of all, the LIFE approach. As I said before, the LIFE approach works in the Kepstrel model here, and because we have like 13 Kepstrel sequences, so this approach will be applied individually, will be applied to all those 13 Kepstrel sequences. Now, before going on to the details of this algorithm, what I like to say is that, so now we have a model to represent reverberation in the Kestrel domain, and next we need to find out a compensation algorithm. So the question is that how do we guide our approach towards? Now see, the problem is that we don't know the room impulse response, we do not know the clean speech spectral values, the Kestrel values, so it's a very hard problem. So in order to guide our problem, we need to study some of the properties of speech which we can apply and guide our optimization problem towards a direction where speech features lie, and specifically this algorithm is based on maximum likelihood. So I use the speech knowledge of the distribution of speech features, so I can learn the distribution of clean speech features, and then I can guide my optimization towards a direction to maximize the likelihood with respect to clean speech features. So this is the speech knowledge I'm using in this algorithm, and otherwise it does not use any knowledge of room impulse response or of the clean features directly, so it works in a blind fashion. So what I'm saying is that so reverberation takes me from a clean speech feature distribution to a reverberated feature distribution, and then I apply a filter to go back from here to here so as to maximize my likelihood function. Now before going forward and showing the method, I like to study this method with small examples, and I like to study that if I take a simple example, then do I get the best answer, or how close I am to the best answer. So here I take like this is a zero mean unit variance, I'm just assuming a signal to be like this, Gaussian here, and I'm applying this simple filter with a one single delay tab, and then the question that I ask is that if I try to find this filter, then what is the relationship between this little p and this little h? So that is the question I'm asking now, and what I would expect is that if I do this, then the little p should be able to cancel the effect of this little h here. If I can do that, then I, at least in a simplified setting, just theoretically I can show that the method is working. Now this can be done simply by taking log likelihood here and differentiating this log likelihood with respect to the unknown p parameter, and what I find is that this little p is approximately equal to minus h. Now and if we multiply these two the filters, we would like the multiplication to be unity, so that the effect is cancelled out, and we see that at least the error is in the second order, it's not in the first order. So at least to the first order this method is working fine. I can ask another question, that what if I have a filter like this, it's an exponential tap filter with exponential filter taps, and I do the same thing, and what I would expect is that this p should be equal to minus h, and in fact it can be shown that this p is equal to minus h, and similarly in this case I can also have an IAR filter, and again I can show that this little p is equal to little h here. So at least in simple settings I can show that without doing a speech recognition experiment, I can show that the method is doing what it is expected to do. Now next I'll apply this method to speech recognition. So to apply the problem for speech recognition, I make an assumption that the speech features are distributed according to a Gaussian mixture model, and I can learn these parameters from data which I have already available, and then I want to estimate this filter here. It has an unknown gain term and these little p terms here, so I need to estimate these parameters. So again, I set up a log likelihood expression here, and then I do a gradient descent, I do a gradient descent maximizing log likelihood, and try to obtain the parameters in a step-by-step fashion.
So what the equation is different from LPC?
This expression?
Mm-hmm.
Here I'm obtaining the filter taps, and I'm applying this on the Kestrel sequences. In the LPC, what they do is that they apply this on the speech waveform by using the correlation terms there, but it is not the same, and
It is LPC on the Kestrel sequence.
it is, but I'm actually not. But this is LPC is not based on maximum likelihood, right? It is based on an error, the squared error minimization. So, and in the LPC we get terms like autocorrelation. So you raise this point. So I would expect that if I have a single Gaussian density here, then I might get the LPC term. But if I have multiple Gaussians, because single Gaussian density reduces to error squared, and then I might get the same term. But because I have a Gaussian mixture model here, then I think the answer will be different. Yeah, a single Gaussian density might reduce to LPC. Yeah. Okay, so as I said before, I mean, I'll skip details here, but I set up a log likelihood maximization criteria and do a gradient ascent from there, and the approach is applied on the different Kestrel features. Now, before doing a speech recognition experiments, I like to just see how the method is working. So here on the left panel, this is a Kestrel scatter plot for on the x-axis C1 and the y-axis C2 here. So we see that the Kestrel scatter plot distorts and it does not match with clean and reverberated, because the reverberation is going to smear the spectrum and it is going to spread out. But after applying the live processing, we see that at least with the scatter plot, these two match better. So I would expect that the performance will improve.
So the likelihood function that you maximize because you are using GMM, so
yeah.
And then it should use EM to update the parameter. Are you using that?
No, the GMM is of course trained using EM, but when I do my gradient descent, I have the GMM parameters, and then I just do a gradient descent, a gradient ascent like.
So without updating the posterior probability of those mixtures.
GMMs, yeah, GMMs are not changed. GMM is trained just from clean speech features, so that's not changed.
You can also, because you are doing maximum likelihood, so you can do several iterations. And then
you mean
each iteration you need to adjust the posterior probability of.
Oh, you mean for the GMMs?
Yeah.
Okay.
As a way to because you need to decide which Gaussian component best match your data.
Right.
And that cannot be determined in prior, right? You need to determine that given observation.
Right.
So that's
see. I did not do that because I didn't want to really change GMMs, because that will probably change the clean speech feature. That will not exactly be the distribution of clean speech features.
I know what you're saying, change the GMM from.
Saying adapt the GMM
if you maximize
to
the likelihood, because it's a GMM, it's not closed form, because you don't know which Gaussian and GMM
that's true.
observation belongs to. So
yeah,
you need to get a soft decision with them.
Yeah, actually, in practice, what I do is that I do classify my single feature vector into each one of these GMMs, like a posterior, and then I used just that. So just like top one, top one.
But that's what
because that really simplifies the problem a lot. I mean, it makes the calculations much faster. I take the most likely for each feature, and then just use that information, discard the rest. I mean, I did experiments and I found that just that works almost well in my experiment, so I don't care about the rest. Yeah.
And you're doing this independently across the Kestrel?
No, it's actually done jointly actually, because the GMM
so you're
is
able to leverage information from one dimension.
Yeah, right. Yeah, it's exactly. I'm not doing independently. It's all joint. So even though the covariance matrix is diagonal, because it's still a GMM, it's a combined GMM, so I'm able to leverage, right? So next I'll present speech recognition results on different databases. So this is one of those on the resource management database, and I compare with some of the baseline algorithms which I worked on, I mean also from different research communities. So some of the baselines are MFCC, CPF is a Kestrel post filtering, and FDLP long-term log spectral subtraction, which I talked about before, and the live filter. So we see that, I mean, going from 7% to 50%, some of the baseline algorithms that do not really provide a lot of benefit. And this is done on clean, the training was done on clean speech. I'll also talk about matched condition later on. But the improvement here is limited to like 15% at max, like that. But the improvement by using live processing is up to about 40% here, 43% relative reduction in error rate, and also similarly here. So even though the problem formulation is simple, the analysis is simple, I'm able to leverage the fact that I represent reverberation in the Kestrel feature domain and directly apply my techniques there. And I'll next show some examples of the,
So even though the training was clean, did you put any of that training data through any processing?
Yes, so I feed clean speech also through my processing. Yeah.
The other
Yes, all of them.
So you did lifelong cross-factor destruction, clean training data.
On the clean also, yes, yeah. I mean, I haven't especially looked for LTLSs, but in general, I find that, yeah, right. In general, I find that it is also important to pass clean speech also through the processing. Even if the processing does not do much, even if it just reconstructs a little bit, I mean, it provides a better match. So yeah, all of these were passed through all these processing. Okay, so in this example, I plot the frequency response that I get of the filters. So as I said before, I'm trying to estimate the filter parameters. So these are 4 different utterances for the same reverberation time, so 300 millisecond. So the first thing what I expect is that the frequency response should have a high pass nature, because the room impulse response has a low pass nature. It smears a spectrum, so it's like adding things. So the inverse frequency should have a high pass nature, which I do find that exists here. The second thing I expect is that even if the utterances are different, because the room impulse response is same, so I would expect that these filter responses are almost same for all the different utterances. If I could do that, I mean, that means that I'm learning the algorithm is not as much dependent on the speech utterance, it is more dependent on the room acoustics. So as we see here, I mean, figuratively looking at these utterances, we see that they are it is trying to do that. And to test this specifically, what it did is that I took 20 different utterances and I took an average of those 20 utterances. I took an average filter, and then I applied that single average filter to all the rest of the utterances. So here is an example of the average room impulse response for a particular condition, and here are the results. So this is MFCC, this is life, which was obtained by individually working on the utterances, and this line is obtained by just applying an average filter, which is learned from 20 utterances, and applying that average filter to all the rest of the utterances. So I mean, this does suggest that even though there is a bit of an error, I mean, mismatch here, but in general I'm learning the room acoustics and more and the speech less, because just from one filter applied to that particular condition I'm working as well. Okay, so I did experiments on different databases here. This is on a large room but still simulated, and this result is on from an ATR database. The ATR database was collected in Japan, where they played out audio from timid database through a microphone and collected them in a different rooms. So so this database, actually this experiment is a little different, and they also collected room impulse responses in different rooms. So this experiment was done by taking a room impulse response from the ATR database and applying that through my clean speech and get reverberated speech. So this actually this is still an intermediate result. This compares the difference between simulated room impulse response and an actual room impulse response. So we do see that the improvements definitely hold up even for an actual room impulse response. So far I talked about clean condition, where training was done on clean speech and testing across different times, different reverberation times. But as we have noted recently, actually not very recently, that is not the best thing to do. And people in industry especially are doing training across all the different conditions they can find, across all noise and reverberation probably. They mix it in a training database, and then it's like a multi-style training. So the question is that, do algorithms hold up even in matched condition or not? So so that is what I'm going to evaluate next. So to do that, I did this experiment here. I took 2 different rooms and got room impulse response from them, and this is from the ATR database, and I have all these bunch of conditions, and from these I did multi-style conditions. So the training database has room impulse response from different rooms and also different conditions. Actually there are more results, but I'll just present one result here. This experiment was specifically done by training on room 1 with these reverb time, these reverberation conditions here, and then testing was done on a large number of different conditions here. So these are on room 1, the room 2, and the J. This is from ATR database here. So I mean, the first thing which is very noticeable here is that the clean condition performance improves drastically even for MFCC. So sorry, I mean not the clean, I mean the baseline performance for MFCC shows a huge improvement. I mean, when I did this experiment first, I think I was surprised to see that, because just a matched condition shows about 60 to 70% relative improvement on MFCC. And but at least a good thing is that the applying the live processing further. So these are like highly matched condition. This database is from room 1, nearly same reverb times. So in these highly matched condition, I'm still getting like 15% relative improvement, and these are slightly less highly matched. But still, we can see that the MFCC performance still shows a huge improvement. Even the matching is not not strict. And but in these cases, the live filter provide like 20% relative improvement. So the point is that the improvement is slightly less if the matching is very strong, but in general we cannot really expect that in a practical setting, because we cannot really have a perfect match in any case, right? So whenever the matching is not totally perfect, we still get a very significant improvement even in matched condition as well.
Still resource management?
Yeah, this is still resource management.
So the GMM live is also trained on the same set.
On the same database, yeah, on the same set, right? Yeah. Actually, I'll answer that later. Okay, so this is on the sort of the same experiment, but on a Wall Street Journal experiment. So in this experiment, I do training from the room R1 and these reverb times, and I do testing across room R1s here. So again, I noticed that one thing noticeable is that the clean error actually increases here, as also in the previous experiment, because now the training is done across a variety of room impulse responses, so the clean performance actually degrades for the baseline MFCC. But again, the live processing shows improvement on clean condition here. Yeah.
How do you see word error rates?
This is word error rate.
Yeah, from purple 10 to
Actually,
red.
Okay, sorry, I should have clarified this better. So actually there are two sets of experiment here. One is without matched condition and one is clean condition. So here, as you can see, these two experiments are training on clean, and these two experiments are training on matched condition, right? I should clarify. So we actually need to compare how much of improvement we get over matched condition, and then also compare how much this is further better over the clean training. So as I said before, yeah.
The match condition is matched on the zero reverb time.
No,
It's multi-style.
it's multi-style actually. Yeah, there are three sets here, and this is all the three sets there, right? It's not just one. Actually, I'll also show that. But anyway, so I said that the clean error increases, but the processing improves here, and here and so here also the processing is improving, and this is on Wall Street Journal experiment, about 15 to 19% relative improvement on an average.
So can you make a comparison with the MRRs, because this is also can be considered as an adaptation?
No, that's true. Actually, I'm still to do that. I'm scheduled to do that sometime before but yeah, I have to do that actually. I haven't been able to do that so far. Yeah, exactly, because this is like an adaptation where given utterance, we are given some knowledge about the speech features, we are adapting it. But I think the key difference is that in MLLR, they do a linear transformation, but here I'm doing a filtering transformation. That's the key difference.
Multiple regression. If you use regression tree, you can, to some extent, it's also linear.
Uh-huh.
You can also.
Okay. Yeah. That's true. Maybe, yeah, I'll look into that.
So if you look only at clean, not matched training,
Yeah.
at R1 500,
Yes.
your wear rate basically from a 10, now goes to,
Yeah.
after live it's 90%.
That is training on clean.
Yeah.
But if you do matched,
that means if your life is doing a perfect job,
it's not doing a
it could
perfect
be
job.
10%, right?
Yeah.
So it's not. So it seems to me it's very far from perfect.
That's true.
90% really you didn't
Yeah,
do really a lot of things.
Yeah, that's true.
How do you interpret this? Does that your model is too coarse,
Yes.
or
Yeah, I think one of the reason is that my model does not, it fits well if the reverberation time is not very high. But if the features are very, very, very highly reverberated, then the model is not doing a great job, I think. That is how I interpret this. And especially if the database is if you do the same experiment for resource management, we see that here it's, in the resource management, here it's like going from about 70 to about 40% here. actually, yeah, this experiment is the same thing for resource management. So here it goes from about 80, less than 80 to about 40. So here the reduction is very large. So there are two things here. The database itself is very difficult, and the complexity of the reverberation, I think, is my model is not perfect, of course. I think, yeah, that's the point.
Pieces. So even though you say you are doing EM sort of on this, right? You have to pick with Gaussian, right? And so I imagine that as the data gets more and more reverberant, it's harder to find the right Gaussian.
And then.
So you could. I was just wondering if you've ever run like an oracle. Since all your data is synthetic, you can actually like cheat and figure out what is the optimal Gaussian for that, and then for like or even just use the clean speech as the target rather than GMM.
I see.
And apply your model.
Yeah.
And that would say that's the best your model could do with the likelihood. If the target observation is perfect.
Right.
Have you done that at all?
No, I haven't done that actually, but I did a slightly different version of that and similar flavor. So what I did was that I looked at the Gaussian component that I pick in clean case, and then I looked at the Gaussian component that I pick in live case, and doing that before live processing and after live processing. So what I find is that if you look at the Gaussian components that get picked after live processing, they match better with that in clean conditions. So yeah, I did that experiment, but I don't remember exactly. I would expect that the same thing holds better if the reverberation time is small, but if that will probably not hold that well if the reverb is very high. Yeah. Actually, I will extend this method later on also. So okay. Anyway, so this is where training was done on all the 3 different reverb times. And next, I was also curious about another experiment where I did training on just one condition. So I just reverberate my database with just 300 millisecond of reverb time, just one condition, and I compare this with where we have 3 different cases here. So just to be curious if there is an additional improvement in a perfect matched condition. So actually, this experiment here is a perfect matched condition here because the experiment is trained on this condition, this is a specific condition, and they tested on the specific condition here. Yeah.
So with this experiment here,
yeah,
it seems like previously this MFCC number would beat life.
Actually, it will be this one. This is MFCC, and
Yeah.
this is trained.
But the order used to be that like MFCC and then life was a little better, and then match condition was even better than that. Am I remembering the slide wrong?
Actually,
So
there is a bit of a difference here. These results are clean training actually. Yeah, these 2 are on clean training.
Oh, okay.
So now,
so this yellow and red.
yeah, actually,
are now
yeah,
blue and
these 2 are right.
The blue and light blue.
Oh, okay.
Yeah, right. Yeah, so those 2 become here. So the only difference is that here the matched was a multi-style matched, and in these 2 cases the matched is a very strict matched.
Okay,
So
that makes
that's the
sense.
thing.
So the gain is just from.
Yeah, the gain is just from live processing. And note that this shoots up very high. The clean error shoots up very high, as expected here. But anyway, the point is that on this database, even on very strict matched in reverberation, there is like a 15% relative reduction here. Okay, so finally, in conclusion, so live processing, it is an adaptive solution. It does not require any prior information. It builds on just the information of clean speech and distribution. And we get high pass filter which mitigate the room impulse response. Now next I'll talk about the non-negative matrix factorization, which yeah, sure.
The other one. So what you're estimating is an IIR filter.
In my live processing, I estimate an IIR filter. I actually also did for FIR filter. I get good benefit in FIR also, but IIR provides little better benefit. The reason is that in IIR I need to have fewer parameters to. If I have more parameters in the FIR, I think
Do you have any way to control for
number of parameters?
stability?
So
it's
yes.
possible to get
Oh yes.
get
Yeah, that's true. It is possible to do that, and what I currently do is that I check for that, and if I violate my stability condition, I just pause. This is what I do right now. But I do that because in my experiments I find that the filters are stable. Actually, in all the experiments I had so far, I checked for that. It actually very rarely I found that it's not stable. So I mean, there is probably some reason why, but it just experimentally turns out that it's stable.
So for that question, then,
Sure.
what is the comparison? You know, of course, you compare with the basic MFCC, right?
Uh-huh.
So suppose you use a much simpler high-pass filter
Uh-huh.
rather than doing the estimation.
Oh,
and
yes.
so on.
Yeah.
And that would be a different baseline, right? Do you have
Yes.
any thoughts on that?
Actually, Professor Rich, he did ask me that question some long time back, and I did do those experiments. Because if you look at the filters here, they look like a high pass. I mean, they are a high pass filter, right? So he did ask me to try to fit this filter by using one pole or two poles. Try to empirically fit this by a single pole or two pole. And I try to do a good job at fitting them. And what I find the result is that the result is actually somewhat intermediate. I mean, that's like, it does not really achieve this much, but it is somewhat intermediate, like less, not even half. Yeah, that does benefit, yeah, I mean, answering your question. But it does not reach this level.
So why would you limit yourself to one or two poles? Why not go further, like doing a full Rasta normalization or?
Okay, I don't know. I think I did not do that.
You can do design multiple whatever coefficient filter.
Yeah.
And minimize the water rate with respect to those filtering coefficients.
Yeah, I think the reason I did not do that was that because had I done that, that will be like very, very specific to one particular reverberation time. So I wanted to do that to study how it works, but in practice I can't really do that because I don't know the room acoustics phenomenon. So that is why I did not take up that further. But even for a two-pole filter, I mean, I was getting this fit to a considerable extent. But yeah. Okay, so the NMF also works on the similar framework that I talked about. It works but instead of working in the cepstral domain, it works in the spectral domain. But again, the model is a convolution in the spectral domain. So again, notice that what we get is the cap YS sequences. We don't know the cap H or the cap X sequences, and we have to split terms. And there are obviously many ways in which the cap YS can be split into these two terms here. And again, to do a better job, we need to specify some constraint, something that we know about the signal of interest here. So in the non-negative matrix factorization, I use the sparsity of the signal, sparsity of the spectra as a feature of speech spectra, and then I use the non-negativity of the spectral values as an additional thing, which is obvious. So again here, actually, the problem formulation is trying to solve a mean squared error objective function here. So I'm trying to, given an initial estimate of the cap X and the cap H, actually I think there is a multiplication here, sorry, this is not minus. So I'm trying to minimize this error squared criteria subject to a sparsity constraint. So I want that the features, the spectral should have a sparse value. So only few of the values should have a large value and the rest of the value should be small. And again, this is solved in a gradient descent fashion, but we need to ensure that the values are non-negative. I mean, there's not. I've skipped equations here, but eventually it turns out to be a multiplicative update. And I mean, this convolution is in the spectral domain,
not in the time domain.
Not in the time domain.
So what is the motivation? Can you?
Yeah. So I discussed, right, in the feature domain. When I was discussing about this, I said that I'm trying to represent reverberation not in the time domain but on the feature domain, because the speech recognition actually works on the features. And then I showed that I can represent reverberation actually happening in time domain, in the spectral domain, with a small error.
Sorry.
Yeah.
The spectral domain or the Mel spectrum?
Actually, it's both. Yeah, I mean, initially it is in the spectral domain and then also in the Mel spectral domain.
Your definition of convolution is not, it's across, is it still again across a spectral bin?
No, it is on one frequency channel.
Right.
So yeah.
You're treating all samples, but it's still a time domain convolution.
Yes.
Treating a single bin over time as a time sequence. It's not really convolving.
No. No, I'm treating each of these. I'm treating that each of these, each of those the filter, each of the short duration power in a particular frequency channel, they are convolved
With each other over
with
time.
each other. Yeah.
So it's a
over
time
time.
sequence.
Yeah, it's a time sequence, right?
Current sequence of log spectral.
Band.
Not log.
Yeah.
The millispectral
Linear.
values. Yeah.
So what is the theoretical ground for this? Why convolution is the best model there?
The theoretical ground to some extent lies in like here. So I did try to to show here. So this is what I'm doing. So I'm representing the blue line with the red line, and I'm saying that even I'm representing convolution in time domain as a convolution in a spectral domain. There will be some error, but the error, as we can see in a practical application, is a small, and this gives us a simpler model, but it lets us do parameter estimation and de-reverberation application.
But my question is, you don't have to do the convolution.
Yeah.
You can do, you say it's multiplication thing or additive thing. You can also move the two lines, closer.
Yeah.
So why the convolution is particularly indicated?
I can use multiplication, but then I have to use a very long feature vector. I mean, the duration of the analysis window should be up to second. This is what was done in the LTLSS, right? The analysis window was 1 second or like that. But right now I'm working in a small window. So as you can see, because the reverberation will smear energy into future frames, so energy will overlap. So energy from past sample will overlap into future segment, right? So this is an additive phenomenon. I mean, this is not completely linear. There is also a noise term here, which I'm ignoring right now. As you can see, because if there was no noise, these two lines will match perfectly. But there is an approximation error. So, but still a good thing is that even with small approximation error, this is a good model. So I think I was... Okay, so coming on to your point, which I think Mike asked. So this is right now my the NMF compensation framework. What I do is that I window, pre-emphasis framing windowing, and this is either a magnitude or a power domain. There, I can do it in either, and then I can either apply the NMF processing on the frequency, on the Fourier frequency channels, or I can apply the same processing in the gamma tone filter bank. So there are different flavors of this algorithm here. And to do into gamma tone filter bank, I have to apply this gamma tone filtering and then apply this NMF here, and then I reconstruct by applying actually an inverse transformation here. So the question is that which will be better? So will working in magnitude domain be better, or will working in a power domain be better, or will working in the gamma tone domain will be better, or working in the Fourier domain will be better? So these are the questions I am going to take up. Yeah.
When you do NMF, so what's the P you set? The norm.
It's L1 norm actually. Yeah. I mean, I did do experiments with changing that parameter, but I find is that it does not really change a lot. Maybe I need to do more experiment with that. I have not explored that a lot. This is what we just chose, and this I chose some by changing small parameters, but that didn't really change a lot. Okay, so this is an example of applying this processing in the magnitude domain and in the gamma tone filter domain. So this is the reverberated sequence here. So we see that by applying this processing, the processing helps to remove the spectral smearing, and we get sharper, cleaner spectra. Okay, and in this experiment, yeah. Oh, sure.
This is before and after.
Yes, this is before and after. Yeah.
Give me the last date on Flasher's Cat 4 equipment casualty. Give me the last date on Flasher's Cat 4 equipment casualty reports.
I forgot, it's always hard. Inappropriate route.
Right, but if you listen to it carefully, I think it's not perfect, of course, but it does help in that direction.
Second one sounded more like this one.
Yes.
Yeah, exactly.
Okay, that explains. Okay, so in this experiment actually I'm comparing different versions of this algorithm, applying in the Fourier domain versus applying in the Gameton domain, applying in the magnitude domain versus applying in the power domain. So the first thing I would expect is that if I apply the processing in the Gameton filter domain, because I have only 40 Gameton filter versus about 256 Fourier frequencies, so I have the dimensionality is reduced a lot, and then because the Gameton filters are designed to mimic they focus on the frequency components which are more useful for speech recognition, so I would expect that the performance is better. And additionally, what I find is that if I do the same processing in the Gameton filter domain, the approximation errors is smaller. So earlier I talked about the approximation error. The approximation errors is smaller in the Gameton domain because it does an averaging, right? It does an averaging over the entire frequencies, and then so because of that, the some of the noise gets smoothed out. So there are lots of benefit in Gameton domain here. And starting with this is MFCC baseline, and these are for the NMF algorithms. So we see that I think these bunch are for the Fourier frequencies. So these bunch are Fourier frequencies, these bunch are for Gameton frequencies. So on an average, the Gameton frequencies error is much smaller. And then I also compared this, let's talk about the Gameton frequency here. I also compared with the magnitude domain versus the power domain versus magnitude domain. So I find that applying the processing in the magnitude domain gives a smaller error. And again, I did try to look into that, and I found that the approximation error was smaller in the magnitude domain, like that. So, and there is one more experiment here which is labeled -H. So -H means I apply the same filter across all the frequency bands. So I was interested in comparing that understanding and see, can I apply the same filter to all the frequency bands, and if I apply individual filter to all the frequency bands, how much additional improvement do we get? I mean, of course we expect improvement, but the question is that how much improvement we get. So as you can see, so we get like from here to here, which is still like a significant improvement by applying the filter on all the different channels on top of the rest of the improvement. Yeah.
Is there a theoretical basis why NMF would work better in this case for magnitude versus power? Or is this just an empirical result?
This is sort of an empirical result. What I tried to see was that I looked at the approximation error. I mean, you remember that my model has an error. So what I empirically found was that the approximation error is about 13 decibel. I mean, the signal power, the noise power is 13 decibel down signal power in power domain. But in the magnitude domain, it's like 17 dB. So it's the approximation error I empirically see is smaller. I mean, I think that is one of the reasons. Okay, so these are again on resource management database, and here again I see that there is a very sharp improvement in performance here. This is clean condition training. And these experiments have been done on ATR. So this experiment is done by simulated room impulse response using ATR room impulse response, and this is using the ATR database, actual ATR database which was collected in a room. So we see that the improvements holds up in both the cases. Actually, they are not directly comparable because this room impulse response is not the same as the room impulse response here. Yeah, I think the database didn't have that probably. But anyway, we see that the improvement holds up in real collected speech as well. And another thing I wanted to show was that
she had your dark suit in greasy wash water all year.
Actually, this also has a noise if we listen to it carefully. So the database also has an additive noise here. So the point is that even if there is some additive noise, even in that case, the performance does not blow away. I mean, the algorithms still hold up even if there is an additive noise.
She had your dark suit in greasy wash water all year.
I think the speech may not sound that great, but still speech recognition accuracy definitely holds up. And because the problem is that many of the algorithms that we design for de-reverberation, some of them are so specific only for the reverberation task, and even if there is small noise, they don't really hold up. So I don't want to go into those directions, I mean, so, okay. These are again RM matched condition experiment. So again we see that the baseline improves a lot, but we still get additional improvement by, this is again a multi-style condition. It has database from all these conditions here. So again the improvement is about 15 or 20% relative reduction in error rate here. Okay, so I talked about de-reverberation algorithm, I talked about spectral convolution representation, and then I'll briefly talk about a noise compensation algorithm, which I find very useful. So it works on an additive noise model. So before going to talk about that, I'll briefly talk about the delta Kepstra features. So conventionally, initially we have like 13 MFCC feature here, and then we apply delta Kepstra feature and double delta Kepstra feature to have a 39 dimensional feature. And what we find is that those features are very important for a speech recognition. So, and this is an example for that. So this is on real world noise collected. It's still simulated speech. I mean, speech is added to noise, but we see that adding delta feature improves like 5 or 7 dB threshold shift. So the point is that delta features are very important for speech recognition accuracy, and even the clean performance improves here. But so the next question is that the best we can do? And the question is that what is the robustness of delta features? So to do that, this is an example. So on the top panel, this is clean speech, and this is noisy speech in 0 decibel. This is like spectral power plot. This is a log spectral power plot, and this is the delta feature that we can obtain from here. So what we would expect is that if the delta features are robust, these two should match very well, if they are very robust. But I mean, as we can understand, because we are applying a log compression here, the high energy values will be very matched, but the low energy values will be very little matched, and because of that, the delta features are not really robust to noise, and they don't really follow the clean speech spectral features. So there is a problem here. And so the next question is that what better can we do? And in my work, what I mean, as we can see that this blue line is the power spectral plot for a speech, and this is for a noise, real world noise. And what I find is that a lot of the noises that we have in real world, the dynamic range is not as high, but the speech power has a very high dynamic range. I mean, the speech energy values change like 30 dB between speaking and non-speaking, but the noise generally changes like 5 and within plus minus 5 decibel. So we can use this cue, and what we can do is that noting, and also note that speech is very highly non-stationary, but in general, I mean, the same point, noise is relatively stationary. So what we can do is that we can apply a temporal difference operation directly on the spectral values here. And what I do is that I pick the delta operation here on the MEL filter outputs. Now, if I do that, I'm going to have some more things that I need to work on. I'll talk about that later. Especially a non-linearity I'll have to apply, because the things become negative if I apply a difference operation in the spectral values. The things are no more non-negative. So I need to do something for that. But anyway, I'll like to figuratively show how is this helpful or not. So this is the same plot that I had before, and this is the plot I get by applying the temporal difference operation directly on the spectral here. I mean, as we naturally expect, if we apply a temporal difference here, whenever the speech energy changes very fast, because the speech power dominates, so we will get a strong following for the speech energy. But whenever the speech power is not changing, things are relatively stationary here. So anyway, the things are stationary, so the values will be nearly 0. And so we are, as we can see here, I mean, we nicely show that applying temporal difference here shows a lot of benefit. And so this plot was done by taking a short duration power over the entire bandwidth of the signal, and these set of plots are for doing the same operation over at the output of 10th MEL channel, so just one frequency band. So again, this is speech, this is noise, this is speech added to noise, and these are the conventional thing, applying log and then applying delta spectral values here, and this is applying delta spectral values directly on this sequence here, and then from here to here I have to go. Okay, from here to here I have to go. This is applying a non-linearity on this. So the non-linearity, what I find is that these features are not. They have like a super Gaussian distribution. They don't have a Gaussian characteristics. So we can't model them by a Gaussian mixture model. So we have to apply a non-linearity to let them be modeled in an HMM framework. So what I do is that I take this sequence here and I make the histogram Gaussian. This is what I do. But again, I can later I need to improve this a little bit, but this is what I do right now. I make them Gaussian so that they can be modeled by a GMM. Okay, so what we have achieved is that we are by doing delta spectral, we are still able to track the changes in the speech. We are able to attenuate changes in noise, and it also emphasizes the speech onset part, because speech onset, I mean, it has been shown empirically that it's very important for speech recognition, and because the speech because it's a difference operation, so it is going to emphasize the speech onset part. And there is a non-linearity here to make them modeled by a Gaussian mixture model here. Now next I will compare the result using my delta features and then the conventional way of doing delta feature. So as we notice, there is what we have done is that we haven't added anything fundamentally new, but what we have added is that we are doing a temporal difference operation in a domain which is better, and then we apply a non-linearity to make them Gaussian. So that's it. And these are for a number of different conditions here: white noise, music, real world noise, and reverberation. So we see that just doing that provides us a lot of improvement here. I mean, especially for music noise and for real world collected noise at 50 dB, we have like 7 or 8 dB, I think 5 or 7 dB threshold shift here. And it also works a lot in reverberation.
Utterance specific?
Right now actually it is utterance specific, but what I mean, we can learn that Gaussianization from clean speech and then apply the same, because actually there is not fundamentally different across different utterances. So we can learn the non-linearity shape basically for a clean probably, and then apply the same for all the different conditions. I haven't done that, but yes, yeah.
So I think, ironically, that someone from like ATR and I think NTT basically proposed this reverberation like a couple of conferences ago. Maybe
Okay.
So I just wonder if you're familiar with that work and there's differences.
I don't know exactly, but I mean, I have done some literature survey, and what I see is that what people, there's one paper, Kaliwal, I forget the name, Kuldeep Paliwal, yeah. So he has a paper, and what he does is something similar, but then he applies a mod operation to make them non-negative. So he takes a difference and then applies a modulus operation to make them non-negative. And I did do my experimental comparison with that, but that shows some improvement, but that does not really show a lot of improvement, because once you take mod, you mitigate the differences between rise of energy and fall of energy. They become same. So I think that was the closest which I found. Yeah, sure. Okay, and this is the same thing where I compare MFCC and with the delta Kepstra feature versus delta spectra feature, and I compare with an advanced front end. This is from ETSI database, ETSI Institute. So we see that comparing this red line versus this blue line, this is the improvement that we get from advanced front end. So advanced front end shows a lot of improvement over baseline. But if I replace the delta Kepstra feature with the delta spectra feature, we see that even the baseline MFCC feature works almost as well as the advanced front end system here. So the point is that we are really getting a lot of improvement by doing little work, by changing the delta operation, and we are approximately obtaining the gain which advanced front end provides across different noise and reverberation. Okay, so yeah.
What's the number of mixtures you use in your model for this experiment?
Actually, here there is no Gaussian mixture.
Yeah.
There is a Gaussian mixture for speech recognition in the HMM. Is that?
Yeah. So HMM, how many?
I think 8. For resource management, we use 8. And
so because that actually my question is the motivation for your Gaussianization. So I think if you have enough number of GMMs, number of Gaussian mixture are large enough, so probably can approximate any distribution. So the motivation for Gaussianization it may tie to the number of Gaussians that you use.
That's true.
Maybe it's too small.
Yeah, that is possible, but I just use baseline. The reason is that I think that if I increase the number of distribution, I'm actually adding a lot more parameters into my data, and I might overfit. And that is what I think, that I can easily apply a non-linearity. It's just one non-linearity. It's just like a log non-linearity, but a different non-linearity which makes them more closer to Gaussian. So that is the approach I took. Rather than increasing parameters, I thought it is better to do it on the features themselves. Okay, so right now what I'll try to do is that I will also try to understand how much of benefit this noise compensation can provide without doing a speech recognition experiment. So I'm interested in knowing how much of benefit do we expect by doing this compensation, and how much noise is actually reduced analytically. So to do that, I can consider white noise, for example. I can consider a segment of white noise, and I can find out the power p. This will be a random variable, and then this p is a chi-square distribution with n degrees of freedom, but we can treat this approximately Gaussian if n is large. And then what we can see is that this p is approximately distributed to be Gaussian sigma square, and this variance here. Now this can be split into an AC power and a DC power. So the DC power is just mean squared, and the AC power is this variance here. And now to an approximation, what the algorithm will do is that it will definitely remove the DC power, because we are subtracting. So the DC component of the signal will be totally gone. And to that approximation, the reduction in distortion power can be obtained from this expression here, which turns out to be this. And for a 25 millisecond, n is 400. And we can say that we expect that for a white noise condition, the white noise will be reduced by the noise power associated with a white noise signal will be reduced by 23 decibel. So this gives us some sense into where we are heading to. And we can do the same thing for white noise, real world noise, babble noise, music noise, and speech. Actually, white noise is theoretical, but these are experimental. So I can take a segment and do the same thing and see what happens. And so the blue line here is what I obtained by doing a speech recognition experiment. So I would expect that at least the trend should be followed. The two are not exactly same, because I'm not comparing same thing with respect to another thing, but at least I would expect that the trend is followed in the two, which I to some extent see that if these values are high, these values are also high, and they sort of decrease. And the good part of this analysis is that it tells us, without doing a speech recognition experiment, it suggests like how much of benefit we can obtain from an experiment, from a processing. So finally, a joint noise and reverberation model. So as I said before, this reverberation model has an approximation error, and we can actually account for that approximation error here by an additive noise here. And this also acts like a unified model for joint noise and reverberation. So if the data also has a noise in it, we can actually account for that noise here itself. So this also acts as a better model for reverberation, and also for a joint noise and reverberation model as well. And then compare this with the prior model which people worked on. So prior people worked on this multiplicative model and an additive noise here. And right now what I'm doing is that I'm replacing this multiplication by a convolution here. So I have more parameters to estimate and work with. So next what I will do is that to compensate for this filter I apply NMF, and to compensate for this noise I will apply the delta spectra features. Anyway, this is the framework I'm working on. So I have this I have this cap YS. This is what I get. It has both reverberation and noise. I apply first NMF. NMF reconstructs speech signal. And then I pass it through the Melee spectra, and from Melee spectra I get DSCC features. I append these two. So these are again 39-dimensional features, but they have compensation for both noise and for reverberation. Not totally correct, but yeah, they do. And so the question is that how well they work. So this is an experiment with only reverberation. So this same thing I showed before. So these are the results with what I showed before. So just applying NMF. And now if I also add the DSCC features, I get additional benefit here. Actually, I noticed that this clean performance here increases. I need to look into that more carefully and see what's going on there. But at least in the reverberation, we see that there is a very sharp improvement at even all these conditions here. Now this is the same experiment where I passed signal through a reverberation, then I added noise, a real world noise on that. So it is reverberation and noise both. And we can see that the baseline MFCC features degrade very heavily if the data has both noise and reverberation. And applying the NMF shows improvement, and this is only applying DSCC shows a lot of improvement, but combining NMF and in a joint fashion shows additional improvement over the rest. I mean, yeah, sure.
You say that you, forward one.
Oh,
Yeah, there. You say that you created this data by first reverberating the clean speech
and then adding
noise.
Yes.
Is there any issue here with the noise not having the reverberation as if it was from the same room? That is, if you added noise and then reverberated it, would the algorithm work the same?
Actually, I haven't done the experiment, but this noise was collected in a real world setting across.
What does that mean?
I mean, it was collected in a restaurant and it was collected in a factory. So the noise sort of has some reverberation, but it's not exactly the same. It's different. Yeah, that's true. It's different from the edge filter. I will probably need to do that experiment. I did not do that.
So do you think it would affect the experiment, or do you think it would not affect? What's your intuition?
I don't think that it will affect the experiment. I think that I will still get significant improvement from there. Okay. I think so. Yeah. Okay. So finally, I'll very briefly present a profile view lip reading experiment. So the idea is that so we can combine audio features with the image features. And so people used to work on frontal view images and extract features, but in one of the experiments I collected profile view images and tried to extract features from the profile view image of a person and tried to integrate them. And so this is the images which were collected from the side as well as from the front. And I'd like to briefly show the so sort of these are the images which were collected, and I'm working on these images. Okay, so and then everything is extracted automatically. So the features which I define here are the lip protrusion features, because I have a profile view image. I can find out the movement along the protrusion direction, the horizontal direction here, and then I can also find out the lip height, the movement in the vertical direction. And note that the lip protrusion information cannot be obtained from a frontal view image, because it's the movement which this information cannot be extracted in that direction. So this gives an additional information from the profile view images, and these are the processing steps. I'll just skip this, and then anyway. So these are the speech recognition experiment done on a different database. So we see that this is frontal view width parameter, frontal view height parameter, profile view height parameter, and profile view protrusion parameter. So the key thing which I extract from this is that the profile view protrusion parameter feature seems to be very important for a speech recognition experiment here, and these features were not present in the frontal view images which in the previous experiment. So this adds a lot of information to add, and then I can also combine all this with the audio features, and then try to see that this is a line for audio features, so the performance degrades as the SNR approaches 0, but at least the profile view features stay the same, they don't get affected by noise, and if I combine the two, I get this intermediate shape here. So overall, in summary, I would like to show that a key purpose of my PhD work was to study reverberation in the feature domain, by making approximations and trying to work directly on the feature domain, so that we have a tractable model, we have a simple model, and then we can extract do de-reverberation on those simple model. Then I proposed two ways in which we can use the speech knowledge, one by the likelihood parameter and the other by the sparsity information. I proposed a delta spectral feature to attenuate noise, and then I studied a joint noise and reverberation framework. And then I mean audio-visual feature integration. So these are the different ways in which speech recognition performance can be improved in a real environment. And then anyway, thank you for coming, and it was a pleasure to come here. And the papers are available at my website, and the algorithms are available at the Robust website. So you can take a look. And yeah, anyway, thank you. So we can, thanks. Can have questions.
So I never saw a slide that compared life with NMF.
Okay, it was not there. The life and NMF, they provide comparative improvement. Life is little better when the reverberation is high, and NMF is little better when reverberation is small. But the good thing is that I can do one after another. I can first pass through NMF and then apply live processing. I did not show that slide. Maybe I should have. I mean, and the thing is that I get further additional improvement if I do that. So the improvement to some extent is somewhat additive if I do the both. It's not a huge. I mean, it's not one plus another, but there is an additional like 10% of relative reduction in error rate in that range for those experiment. Yeah.
So for the NMF, so actually you don't need to assume that convolution model. You just use the linear combination of previous of that being a combination of this being and with this previous being and even the future being. You have a matrix, and then you optimize the NMF objective function given this assumption of the mixtures, how the energies are mixed.
Yes.
And then given the constraint that you try to minimize the norm of the recovered X signal. Yeah. So then you can do some kind of recovery of the original signal. I think probably the performance might be the same as way off. So given the assumption of the convolution that you have if you create an interview.
Yeah, that's.
You can do some experiments like this.
Yeah, that's true. I mean, I did start by making the convolution the assumption, but as you can see later, I added a noise term also there to account for the approximation error. And to account for the noise term, I added the noise compensation algorithm. So finally, I represent reverberation not like a convolution, but like a convolution plus noise. And by working in this framework, if I do something to compensate for reverberation, if I do something to compensate for noise, the improvements are additive. Yeah.
I think if you assume convolution, the benefit actually comes from the computational cost reduction of the ease of computation. If you transform that into another domain, like the Fourier domain, something like that, you can get some benefits. I mean, if you just simple assumption of convolution without doing any further transformation of the domain to some other domain, I think you will get this almost the same performance if you just assume a simple linear combination.
Yeah, but I think the question is that because we have to also be careful about the window size. So the question is that because we have to work with small window sizes and do analysis on small windows, so that is also an important thing, and that is why I needed to have a convolution, because then it tracks for the additivity of energy from previous segments into current segment. Is that what you're asking?
If you try to do some additive things, then I mean, you don't need to assume convolution.
Well, I don't need to assume convolution, but the point is that the additive thing is correlated with the speech. So there is a convolution. I mean, the additive is not uncorrelated with the speech. If the additive components are completely uncorrelated with the speech, then it's noise, right? But the additive components are correlated with the speech, and in that case, I mean, I can't treat that as completely additive, because then generally noise algorithms assume that the noise is uncorrelated. So then I think it will violate the assumption. So that is why I think the best thing is probably to have both reverberation, both convolution and noise. I think because this is very generic. I mean, then we can apply the same problem to only noise, to only reverberation, to both noise and reverberation. So it sort of extends the approach, I think. So there are some other experiments here, as like Mike pointed out. So I didn't show many experiments by combining like NMF live, DSAC. So I did those experiments as well, and there are further improvement if I like do some combination, though small. So.
Any other questions? Okay. Thank you, Speaker Again.